So I will continue that today. So if you have any questions from yesterday's things, you can ask me. So the things we have covered yesterday is basically how to explore the time series data, what to do first, like plotting and all those things. And then we have covered some models like AMA model, moving average model, the AR model, autoregressive model, ARIMA model, autoregressive moving average model, and ARIMA model, autoregressive integrated moving average model. And then we have talked about something called something which is called this thing that PCF and ACF, that they are basically nothing but autocorrelation function and partial autocorrelation function. Those things we have talked about. And we have then come to an interesting thing that, well, in case of, okay, just very quick.
Capital V, Vemana, at 1999.
Hello, I request everyone, please mute your
microphone, please. Yeah,
I muted.
Yeah, I just muted him. So we have talked about some of the models like AR model, which is basically nothing but it is an autoregressive model, which basically means that the current value will be regressed based on the previous values. Then we talk about moving average model, which is basically something like I regress X based on the current error and the previous error. Basically, I regressed X, the time series based on the previous error. And we pointed out the fact that in case of the autoregressive model, if I have a shock, it will take some time to absorb the shock, whereas for MA model, the shocks can be absorbed very quickly. And then we go for more general model, which is ARMA model, ARMA model. And this is basically some combination of AR model and MA model. So in this case, the current time series is regressed on the previous time series values as well as previous error. That is basically the model. And then we go for a model which is ARIMA model, autoregressive integrated moving average model. And in this case, the main idea is that we can incorporate non-stationary time series into that, but the previous three models basically talk about stationary time series. And in this case, this I is basically new here, and that basically means that if I take the differentiation of the order T, then the resulting time series will be ARMA PQ. Okay, so that was basically we discussed, and then we go for what is called autocorrelation function, and this is basically nothing but correlation inside the time series. Correlation inside the time series. So we artificially make bivariate data, and from that I will talk about the time series, talk about the correlation, and similarly then we talk about partial correlation, which is basically again a correlation, but when the effect of in between values are removed from the extreme values, and then we try to find out the correlation. And the idea is basically that the main use of ACF and PACF is that to find out which model I should use. Okay, to find out which model I should use. And in this case, we have discussed that in case of ARP model, PACF cuts off at the lag P, but that AR actually decays. Whereas for MA model, ACF, the autocorrelation function cuts off at the lag Q, but partial autocorrelation function decays. And for ARMA model, both of them are decays. Okay, so from there, once we can make, we can transform our time series to a stationary time series. We can plot these two things, these two function, and we can check whether any of these three models is appropriate for that time series or not. With that, we stopped there yesterday, and of course, we have talked about some R programs also. So we have basically talked about some codes in R, and as far as I remember, we come up to line number 46. Line number 46, which basically says that how we basically make that particular time series, that AR passenger time series.
Sir, excuse me,
Yes,
sir.
please.
Sir, have you shared the slides?
Yes, that is shared. Are not you able to see?
Sir, I am not able to see.
No,
right
sir.
What about others?
No, sir.
No,
We are
sir.
not
And
able
me
to
also
see.
no slides visible.
We are not able to see the slide, sir.
Okay, sure. I think somehow the sharing. Okay, let me just stop sharing and again sharing. Can you see now?
We can see the window. Yes.
Yes.
Yes,
Yeah, now.
Yes.
Okay, thank you.
Yes,
There
yes.
are some problem. I just stopped the sharing and again share it. It's working. Okay, good. So, okay, so that is kind of a recap that we had. And then as far as I remember, we have basically talk about how we can do that in R. We talk about how to attach a data, and this is basically a time series data. The class is time series that we have checked. Then we plot the data. We plot along with, we also plot the regression line. And we see that, well, in this particular case, we have some issue that variance. That issue was that basically, well, seasonality is there, variance is changing, mean is changing, all those things are there. So we first try to transform this into a stationary time series, and we did this by taking log and then differentiating it, taking log and then differentiating it. So it looks something like this, and then we used the adjusted DF test to check that whether the time series is stationary or not. So that is, as we discussed, there is a basically hand-on process, like we will do it visually as well as we will do it statistically also. So we are satisfied with that. Well, this is a stationary process. Then we see the autocorrelation function and partial autocorrelation function. And we thought that, well, in this case, basically, we can think of a model which basically which is basically that MA component is not, sorry, AR component is not present, 1 degree MA component present, and one differentiation needs to be done over the log of AR passengers data. And then we basically use the ARIMA function to fit it. And once we have fitted it, this is basically giving me the estimate of the parameter along with the estimates of the standard error. And it also provides the error, estimate of the error. This sigma s square basically kind of a variance, estimate of the variance along with AIC value. So finally we are discussing that what is the use of AIC value, and basically the use of the AIC value is to compare different models. That's what basically we discussed, and we stopped in the yesterday's discussion. Okay, so let us start from here today. So that so as we are talking about, one of the aims for us is to forecast. Okay, one of the aim is to forecast. That means basically in this case, this data we have, this transform data we have, and we basically model this transform data. So we try to first forecast this data. Forecast means that we have data up to December 1960. So can we predict the number of air passengers in the month January of the year 1961? Can I predict the total number of international air passengers in the month of February of the year 1961? Okay, that's what basically we try to do. And that we can very easily do with a package which is called the forecast package. Okay. So the forecast package is basically, I have installed it. So I just incorporate the package here. I just attach the package here. Then I can do this one with a function inside this forecast package. The name of the function is again forecast. Okay. The function name is also forecast. And what are the arguments need to be provided here? The argument needs to be provided here. This label argument I will come later. Let us first discuss the first two arguments. The first argument is nothing but that the fit we have done, the ARIMA fit we have done here. So this fit object has everything about the fit. It has this parameter. So when we try to estimate the future values, I have to give this fit thing here, that fit object here, that ARIMA object here. And along with, I have to give this age. And what is age? Age is basically called forecasting horizon. What does this mean? This means that in this case, I have taken age equals to 12. So after executing this function, I will get future 12 values. So all the total number of international air passengers for the year 1961 will be forecasted after executing this function. So all 12 values, future 12 values can be forecasted. Of course, I can change this value. I can change the value of age based on my need. In this case, just for example, I kept it 12 so that I can predict all the values, all the time series values of this time series, this transform time series for the next year. Okay. So if I execute it, how does it goes like? Well, so how does it look like? Okay, it gives this estimate. Okay, that estimate for the January 1961 is 6.11. Estimate for February 1961 is 6.05, and so on and so forth. Please notice that it is a forecast, so we have the fractional value there, and we can have actually fractional value there, because in this case, after transforming, if you see this transformed data, if you see this transformed one, they actually take some fractional values. Okay, they actually take some fractional values because this is basically the transformed data. So that's why it is basically giving the forecast also coming something fractional. But finally, when we try to forecast the, I go back and finally try to forecast the number of passengers. Of course, I should not give some fractional values because that does not make sense. I should give some whole integers here, positive whole integers as a forecasted value. Okay. So forecast function is very helpful to forecast this one. Just simply this function will forecast what is the next 12 values. I can actually reduce it, or I can actually increase it. If I try to just forecast future 6 values, we can actually do this, and you see that we have next 6 values. Similarly, if we want to forecast next 24 values, that means 2 years, we can also do that. Here we have now next 24 values. Okay, and then we can just, let me go back to 12. Let me go back to 12, and then I can also plot, and plot is a very interesting one in this case. See what the plot is giving us. The plot is giving means that the black part up to this is basically the original data. Then this blue line is basically the forecasted value. Okay, the blue line is basically the forecasted values, and in this case, basically you see that I have a band given here, that gray band. And what is this? This is basically the predictive interval. It is called the predictive interval, and the predicted interval is also plotted here. And to take care of this predicted interval, I have to provide this level information. So it is the predictive interval of 95% level. Okay, it is the predictive interval of the 95% level. And that predictive interval basically tells us that, well, if I predict it again and again based on different data from the same process, then 95% of the time the prediction will be inside the band, this gray band. Okay, so that's why the predictive interval is sometimes very important, because you see that we have some idea from here. The idea is that, let me just increase the size to understand it better. Okay, so the idea is that, see, if you come to this part, you see the band is not that fat, but when I have a peak, the band is quite fat. So what does this mean? This means basically that estimate in the peak are less stable compared to the estimate in this smoother part. Okay, so that's why the band are quite important. That actually gives me some idea about the stability of the estimate, stability of the forecast. Okay, so this way we can estimate it. This way we can estimate it and we can proceed. Okay, so this is basically the way we can do this one. And once we have seen, this is basically predicting the air passenger part, log of air passenger. Now, if I have to go back to the air passenger, then basically what I am going to do, I am going to basically I have to take e to the power of these values. I am done, because I have taken the log of air passenger that is forecasted here. So if I have to forecast air passenger, I have to take just log of these values, log of these values. We are done. Okay. So this way we can proceed. There is another nice alternative way. So little bit talk about that. And before doing that, just let me show what are the values this fit has taken. This fit has taken the values that estimates are basically this, and this is the estimate of the variance, and this is the AIC value. So here I am going to talk about another alternative process, and that alternative process is basically kind of a simpler in the sense that many things are taken care by the function, by the inbuilt R function. Okay, I do not need to do many things in this case. So and for this part, basically again I need the library forecast. Okay, again I need the library forecast. So that has already been called. So that's why I do not need to again call this, but I can execute this function. So first function is basically auto ARIMA. So what is do? See, if we do the ARIMA function like we did here, I have to provide what are the values of P, D, and Q here. Okay, I have to provide what are the values for P, D, and Q here. But the nice thing for this auto ARIMA thing is that I actually do not need to do that, and this function automatically choose the order of the ARIMA. Okay, it is automatically, it will going to choose order of the ARIMA automatically, and it basically choose this based on AIC value. So let me execute this. So I have executed it, and then I got these particular values. So now see that things are quite close. Things are quite close. In fact, we have used that from PSEF and ACF. We have used 011, and in this case also that 011 has been chosen by auto ARIMA function. Then the estimates are exactly same. Then the estimates of variance, that is also same up to 4 decimal places after the decimal, 4 places after the decimal, and finally the AIC values are exactly same. So these two actually doing the same thing. Only thing is that in case of the ARIMA, I have to provide the order, but if I use auto ARIMA, that function, that auto ARIMA function will choose the order automatically, and then it will provide the estimate corresponding to optimal choice of the order. And the optimal choice is done based on the AIC value. Okay, so it basically takes different orders here, and check what is the AIC value corresponding to different orders, and then which has the minimum AIC value that has been chosen, and for that, what are the estimates are given here. Okay, so hope that this one is fine for everyone, and then I can do the forecasting. Now again, I have this fit ARIMA 2. I just provide that, and I have the fit. So fit are exactly same as before, and I can also plot the fit. So there is no change in the plot. So they are exactly same. So yeah, so they are exactly same. Okay, some problem is there. Okay, sorry, there is a T. So the plots are basically exactly same. You cannot see that any difference. So these are the two plots. There is no difference there. Okay, there is no difference there. So they are predicting exactly the same thing. But as I said, it is easier to use. Okay. One more point I should mention with auto ARIMA, see that when I am doing this ARIMA model, I have to take log to actually do this thing, do that, stabilize the variance. But with auto ARIMA, I can also use the data directly. And you see that if I use the data directly, it again do the estimation. And now, of course, the ARIMA model will change because data is actually completely changed. So that is the ARIMA model. And in this case, the estimate of the variance is quite high, and that has to happen because now we are trying to, if I take the log, then basically values are quite small, but without log, the values are quite big. So naturally, variance will be little big, quite big, okay? And again, it provides all the value, and in this case, you see that AIC also increased a lot. But there is no problem in this fitting because I should not compare this AIC value with the previous AIC value, this AIC value, because they are done on completely different time series. This is done over the log time series, but this is done over the air passenger time series. Okay, and then I can forecast, and this forecast actually forecast the air passenger values directly. And again, you see that there are some fractional parts are coming, but in any report, I should not give this fractional part. I should report like this in the forecasted value for the month of January 1961 is 445 or 446. If you round it off because of 6, if you round it off, it is 446. Okay, I should report it like that. But of course, because of the modeling, it turns out to be some fractional part is coming. Okay. So then again, I can plot this one, and now this plot is basically for the air passenger data, air passenger values directly, and you see that the variance is actually increasing. Even from this peak, this post peak is even higher at the high level. Okay, so all those things are coming. So this way also we can do this modeling in this particular case. Okay. So, any question? Any question you can ask?
Sir, one question is there.
Yes,
Sir,
please.
we took the log right to reduce the variance, and we took the difference to remove any trend.
Yes.
So we are taking back log, right? We are taking e to the power again to take into account the variance. But for difference, what we are doing? For removing, we have already removed the trend.
No. That okay. Yeah, I answer your question. I understand your question. Just let me answer. See that in this case, ARIMA, when I am fitting in line number 44, I have not taken the differentiation here. The differentiation is taken care by this I of the ARIMA. Okay. So once I forecast it here, if I take e to the power, I am done because now I am analyzing log of air passenger, not the difference of log of air passenger. Does that make sense?
But in the ARIMA itself, we have done the differencing. It means we have made
No. See, that's the thing. See, ARIMA, I am not differentiating. Actually, if you just let me just go back to the definition of the ARIMA. See, what ARIMA is basically saying, it's basically saying that if YT is ARIMA, then XT is ARIMA. Okay? Now, if I analyze that YT value, then of course I am doing a ARIMA, and if I need to go back to XT, then I have to do the integration. But if I fit the ARIMA model, the ARIMA model is fitted to xt, not yt. So I get the xt directly from there. If I forecast based on the ARIMA model with a non-zero d, that means that differentiation is taken care inside the ARIMA model, and finally what input I am giving to the ARIMA model is xt, not the differentiation of xt, and what output I will get when I do the forecasting, I will get xt, not the log of xt. Does that make sense? Sorry, not log, I am sorry, differentiation of xt.
Yes, sir.
Does that make sense, or should I repeat once again?
Yeah, sir, repeat if possible, sir.
Yeah, sure. So what I'm saying is that, say, if you see the definition basically tells that xt is ARIMA if yt is ARMA. Okay. So one way to do this one, I come to yt and I use a ARMA model to analyze this data. Okay, to analyze the data over yt. One way to do this one. Another way to do this one, well, I will not do the differentiation, but I will just try to fit ARIMA model over xt. Note that xt is not differentiated, yt is differentiated. Now, when I go back, there are two ways to go back. One is that if I use the ARMA model over yt, then based on the forecasted value of yt, if I want to find out the forecasted value of xt, I have to do the integration. Of course. At the opposite of the differentiation, I have to do. The alternatively, what I can do is that I do the ARIMA model, and if I do the ARIMA model, then I will give the input as the values of xt, not the differentiation of xt. And when I forecast based on the ARIMA model, the output is basically the forecast of xt, not yt. So if I use the ARIMA model directly, that means that forecasted values are xt. I do not need to differentiate. Do not need to integrate it. Okay, do not need to do the opposite of the differentiation in this case. Okay, so exactly that's what basically I am doing here now. Here in this case, if you see, when I basically do this test at adjusted DF test or plot this ACF and PCF, I have talked about transformed air passenger time series. And what is transformed air passenger time series? That is basically differentiation of log of air passenger time series. Okay, but when I go for ARIMA model, I have not taken the differentiation here. I have only provided the log of air passenger time series. Okay, and that differentiation is automatically taken care by the model. And now when I forecast based on this model, the forecasted values are the log of air passenger, not the differentiation of log of air passenger. Clear?
Yes, sir. Thank you. Thank you.
Okay, so that's why this, inverse of the differentiation I do not need to do. But of course, if I use, instead of doing ARIMA, if I use ARMA here, and if I provide the time series as differentiation of log of air passenger, then of course to forecast this one, first I have to take the inverse of differentiation, then I have to take the inverse of log, and then I am done. Okay, so that is this. So any more questions? Okay, I hope no. So let us proceed. Okay, one thing that I thought I should mention earlier, but I just forgot to do that. See, in this particular example, what I am talking about, I have basically used a data, which is an inbuilt data, and for that, this data, the class is automatically, we have seen it is a time series class. That was, we have seen this one. That class is basically time series, the TS. Okay. But many times what you will get is that you are getting a raw data. Raw data means that that is not an inbuilt data in R. So maybe you are provided the data in some Excel file, or maybe in some comma separated file, or maybe in text file or some other format. So in those cases, what you have to do, you have to basically import that data from those files. And I hope that how to import those data, you know that. I hope Polash has told that, right? Yes or no?
Yes, sir. Yes, sir.
Okay, fine. So I'm just skipping this. So you can import the data from different files. Now, once you import the data from different files, one of the two time series analysis. First, you have to convert that data into a time series class. Okay, you have to convert the data into time series class, and that we can do using this TS function. And this TS function, using the TS function, and the TS function is basically what is do it. Basically, the function TS used to create time series object. Okay, so the function is used to create time series object. And how we can use it? So just for a dummy one, I am showing you with a vector, but of course that is a completely dummy example. In real life case, you have to import the data from some file, and then you have to execute the rest of the steps. So what we do, we basically, suppose we have a vector like this. So if I execute it, it basically gives me a vector. It basically gives me a vector which having the values 1 to 72. And it is a vector, it is not something else. If you see that class of my vector, you see that it's saying integer, it's not the time series. Okay? It's saying it's an integer class, and so it is not a time series object. It is not a time series object. So I have to convert its time series. So that I can do with this TS function and provide the data. The first argument is the data. Then you have several arguments there. This is basically the starting point. This is basically the ending point. And finally, this is the frequency. So if I execute it, and now if I see this in my time series in my MYTS, then this is in the form of the time series data that January 2009, the value is 1, February 2009, the value is 2, and so on and so forth. Okay? And what is the start value? Start value is actually saying that, well, the first reading in the data corresponding to the year 2009 and month 1, that means January, and the data ends at 2014 month 12, that means December, and the frequency is basically 12 because I have monthly data. Of course, no need to give this one in this case, but because once you give this starting value, end is automatically decided. Okay, so this end actually, if we do not give the end in this case, there will be no harm. But let us keep the end here just for completeness purpose. Okay. Similarly, okay. So this way we can give it, and I don't know. This has been 2 times I have just written it. Okay. So this is basically the idea behind the way we converted given data into a time series object, and this is quite helpful. And we should discuss this one first before coming to all the analysis, but I just forgot. I just mentioned it here. Okay. Now let us go back to the slide and let's start something completely new. Okay. So now we will go to talk about something called residual analysis. Okay, we are something called residual analysis. So what does this residual analysis mean? You say that when I am basically fitting some model, of course I am doing some error there. I don't know whether you know or not. There is a very famous quote by Professor Mahalanobis. I hope all of you know the name of the Mahalanobis, because he is one of the pioneer of the statistics in India. He established ISI Kolkata, and then statistics actually started in India. So he is one of the father figure in the statistical community. So one of the very famous quote by him is that all the models are wrong, but some of them are useful. So what he basically means is that the models are basically approximations. They are not the exact. Okay. So we have some real data, and that may come from a very complicated procedure. What we are trying to do is that we are trying to find out a simplified model so that we can explain some part of the real data. So that's why that they are all approximations. Okay. So that's why when we are doing some modeling, definitely we are going to make some error there. And the residual is basically nothing but the error. Okay? The residual is nothing but the error, and we are trying to analyze it, and we need to basically analyze the error also. The reason is that, see, if my model is good, then error, there should not be any pattern in the error. Okay? Error should be completely random, should be completely unpredictable thing. Okay, so if there is, so after fitting some model, when I got the residual, which is the error in the model, then if there is some pattern in the error, that means my model can be improved, because still there is pattern left, so I can even make some better model so that some more pattern from the error can be extracted into the model. Okay, can be taken care into the model. So that's why the analysis of the residual is an important thing. Okay, so let us, before going into what is exactly residual is and how we can analyze, what kind of analysis should we do, let us first talk about one process which is useful in doing this residual analysis, which is called white noise process. So I am not going into exact definition of the white noise process, but what I am going to give you is some property of the white noise process. So the property is that it is a process. Process means basically a time series or collection of random variables, epsilon t, such that it satisfies these three conditions. What are the three conditions? The first condition is that mean is 0 for all t. Second condition tells that variance is finite and constant, that variance does not depend on t. And the third condition is that x's are independent, and independent, of course, implies they are uncorrelated. Okay, they are uncorrelated. Now, why these three things we are talking about here? The intuition behind that is as follows. Say, if I do my modeling correctly, then there should be the error should have mean 0. Why this is needed? Because if the error has some positive, some non-zero mean, suppose the positive mean, that means some very systematic constant part still there in the error that I can keep inside my model actually. So that actually explains more variability in the data, more better, that will actually give better forecast into the data. Just for example, suppose I have modeled something and finally I got that the error has mean maybe 5. So if error has mean 5, that basically means that if that 5 I take into my model, and if I add 5 to every forecasted value, then the forecasted values are basically much better than the previous forecasted value. That's why intuitively it means that after modeling, the error mean should be 0. That's why this condition is kept here. Why variance constant is taken there? The reason is that, again, if I have variance, maybe variance constant does not mean that maybe data or something look like this. Okay, the variance is changing. The variance is small here, but variance is big here. In this case also, I can maybe able to do something different in the model. Maybe I have not, see that log may not have stabilized the variance completely. So in those cases, maybe we can do better modeling. And in these cases, people use something called arch model or Garch model. Of course, I am not going to address this thing in this particular tutorial, particular talk, but those are there to take care of the variability. Even after doing some transformation, suppose the variance is not stabilizing, then people use these models to stabilize the variance even further. Okay, and that basically means that we can improve our model. And finally, that uncorrelated thing or independent thing that is needed because one error here should not affect the next error here. So that basically means that if suppose they are positively correlated, that means if I have a big value of error here, then the next error will be big. That should not happen. Error should be completely random, something like that. Okay, completely random kind of thing like that. That is basically the idea, and that's why basically white noise process this criteria, these conditions, and that's why people try to say that error should follow a white noise process. Okay, so as I mentioned, these are basically something we should check for the error. Now let us talk about this residual analysis or residual diagnostics. So what is residual? Now you can easily understand residual is basically error. So that means when I do some modeling from the fitted model, I get what is the estimated value of xt, and I know what is the value of xt, and the difference between the original value of xt and the estimated value of xt is basically residual. So basically that means I have the time series x1, x2, so on, so forth. So after fitting the model, fit a model, and after fitting this one, you will get x1 hat, x2 hat, and so on and so forth. And so from this one, you will get E1, E2, and so on and so forth. So E1 is basically x1 minus x1 hat. This is basically x2 minus x2 hat, and so on and so forth. Okay, fine. So these are basically the residuals. So in a time series, if I have capital N number of points, I have capital N numbers of residuals. Okay. So what we try to check in case of the residual, basically we will going to check 4 conditions in case of the residual. What are the conditions? First one is uncorrelated. The thing is that checking independence is very difficult and sometimes almost impossible. So people generally try to check uncorrelated only. We want to check whether the mean is 0 or not. As I mentioned, this is needed because if mean is something positive, we have a bias and that we may take a better model there. We want to check whether the variance is constant or not. Again, the idea is the same, that we can, if the variance is not constant, we can have a better model. And finally, this one I have not talked in case of white noise, but this is important because many analyses based on the assumption that the error are normally distributed. So that's why we try to check whether the residuals are normally distributed or not. Okay. So this ET can be think of a observed value for epsilon t. ET can be think as a observed value of epsilon t, the error. The residuals are the observed value of the error. Now I want to check whether the errors are uncorrelated, mean zero, constant variant, and normally distributed or not. And they are basically done based on the observed value, that is ET. Okay. How we can check these 4 points? The answer to this one, again, there are 2 ways to do this. One is visual inspection and another is statistical test. Okay. So in case of the visual inspection, what we will do? We will see the trace plot. What is trace plot? Trace plot is nothing but, see, I have that ET values for different values of t, from t starting from 1 to up to n. Okay. So the trace plot is nothing but plot t in this direction and plot ET in this direction. So if I plot this, and this is the 0 axis, x-axis or t-axis, then this ET should behave something like that. Should behave something like that. This says that the mean is 0. This says that this is roughly inside a band, so the variance is constant, so stress plot actually for using a stress plot, I can check whether the mean is 0 or not, or whether the variance is constant or not. Okay, so if the stress plot is inside a band along the t-axis in the both sides of the t-axis, then we can visually inspect and tell that visually, I mean from the visual inspection tell that mean is 0 and the variance is constant. Okay, then I can see that ACF plot of ET, ACF
Sir,
plot
one
of
question.
ET. Yes,
Sir,
go ahead.
with this trace plot, we cannot judge the last assumption. Residuals are normally distributed.
That I cannot answer. How can I answer that?
So we cannot judge this particular assumption, right, from this trace plot.
Right.
Yeah.
That's what I am saying. I can only answer the second and third.
Right. ठीक है.
Okay, first and fourth we cannot answer.
Okay.
Okay. Then I will go for ACF plot, and this is the ACF plot of ET, and ACF plot you know, and from the ACF plot of ET I can answer the first one. So ACF plot of ET I can answer the first one because you have seen that in case of the ACF plot it gives some band, and if the ACFs are inside that I can take there is no correlation. So if the ACF plot something in between, then I can tell that there is no correlation. Okay, so these two from stress plot, and the last one I can tell from the histogram. So last one I can tell from the histogram. Okay, so that's why in the visual inspection generally we do this thing, that stress plot, ACF plot and histogram. So you know that in case of normal distribution, the histogram should look like something like this. So you know that in case of the normal distribution, the standard normal distribution is the density function of standard normal distribution look like this. So clearly the histogram should be something like that. Okay, histogram should be something like that, and if it is look like that, I can tell that normally distributed assumption I can also take. Okay, so that's why basically these three plots we generally do, and then a statistical test also we do. Again, the detail of the test I am not going into. That is called Lung box test, and this test just I am talking about the hypothesis. So the null hypothesis is that residuals follow a white noise process. Alternative hypothesis is that residuals do not follow a white noise process. So once we do this testing, and after doing this testing, if we see that the p-value is big and the null hypothesis is accepted, then we are done. We are good. Okay. So as we have done in case of the first analysis, plotting and DF test together. In this case also, plotting of trace plot, ACF plot, and histogram along with the Lung box test together to do the residual analysis. Okay. Is this okay? Does this make sense? Any question you can ask?
Sir, I have one basic question.
Yes, please go ahead.
If we are doing this regression analysis, whether for general linear regression or for this ARIMA, we are assuming some assumptions regarding the errors. That the error should be uncorrelated, the mean should be 0. But if we don't make these assumptions, but our mathematical analysis will remain same?
No. The reason behind this is
like sir, if I give the example of linear regression, let y equal to a plus bx, right? Finding the values of a and b by just minimizing the ordinary least square, right?
okay.
Whether these assumptions or not, the mathematical analysis will remain same.
So the answer to this one is that you have only seen partial analysis. Of course, the finding out the least square estimate, there is no need of this assumption. But if you proceed further, like finding out the distribution of the estimates, finding out the confidence interval of the estimates, to do all those things, you need all these assumptions. Without these assumptions, those analyses, at the standard analysis, are not held true.
But sir, in this case, the coefficients that we are finding, regression
Mhm.
coefficient, in that,
Mhm.
in calculating those, there is no role of these assumptions, right? For further analysis, they are playing the role, but in calculating the regression coefficient, they are not
I
playing any role.
completely agree. In calculating, in doing this, the least square estimate, you actually do not need this assumption. But the interesting part is that you try this one by yourself. You just find out the residual and find out the mean of the residual in case of simple linear regression. You will find that the mean is 0. So this least square estimate automatically forces it to be 0, and that is basically coming from one of the normal equation. When you take the derivative and equate to 0, one of the equation actually telling this the sum of the residual has to be 0. Okay, so that is automatically coming through this least square estimates procedure. But as I said, as you also pointed out, that to execute that method, those things are not needed. But only estimating this thing is not enough. There could be some problem in there. We have to basically analyze that. Just for example, maybe you are fitting a simple linear regression. Why need not a quadratic equation? How can you check that? If you want to check all those things, if you want to do some statistical test, if you want to do some try to find out confidence intervals, then the normality assumption is very much needed. Without doing those things, you cannot, without those assumptions, you cannot proceed further. And another point I should mention here, if you do not take that error mean is 0, the problem is that you have a bias in your model. Okay? And if you do the least square estimation in case of the simple linear regression, the least square estimation procedure force your residual sum to be 0. That means residual mean is 0. Does it make sense?
Yes, sir. Thank you.
Okay. So, so that is this. And now let us check how we can do in R. And in this case, basically the useful function is check residue. That will be residuals. One S is missing here. Check residuals and again this function is in the package forecast. So let us go back to R Studio and discuss this one. So in this case, we have basically forecasted this thing that based on that ARIMA 1 is basically based on the log data, and ARIMA 2 is basically based on the original data. Okay. Now, if we do the analysis in this case, just using this check residuals function, how it look like. Okay. So it has given two things. One, it has given this graph, and you see that here I have both the graph, three of the graph. One is the trace plot, then ACF plot, and the histogram. Along with it has also done the test, Loom box text, and it has given the several information regarding the text. Okay. So now let us try to interpret these graphs as well as this test in this case. So from the first one, you see that 0 point is here, 0 point is here. So it is roughly both sides of the 0 point. But still there is some problem, but for the time being, I am ignoring it. The problem is that here the variance is little high compared to this one. Okay. So still there is some problem with respect to variance, but for the time being, I am just ignoring it because see the range is basically from minus 0.1 to plus 0.1. So that range is not very high. This range is not very high. So that's why for the time being, I am just overlooking this one. And as I mentioned that if you have to improve it, after from this point further, you have to use the GARCH model or ARCH model on this time series, that ET time series. That will improve this one. But as I mentioned, I am not going to address this one here. This is little advanced, and within 2 classes, it is not possible to address. Okay. So that's why for the time being, assume that because this is only in the range is basically 0.2 only. So think about this is quite same. Okay. the variance is same, and mean is 0 is okay, because I am around the straight line 0, that points are equally distributed on both the sides. Come to the SCF plot, and if you see the SCF plot, beginning part, the SCF plot inside the band, and that basically tells us that, well, I can take that errors are uncorrelated, that residuals are uncorrelated. Come to the histogram. That nice thing in this for this state residual function is that along with histogram, it also gives the plot of the density function of the standard normal distribution. And it says that histogram is roughly matching with this one. Histogram is roughly matching with this one. Only thing is that, again, there are some bigger values and some smaller values. These are basically coming from this and this point, and this point actually coming some smaller values and some bigger values. But again, I think there is only one or two smaller and bigger values, so I just do not take care of that, because the length of the time series is 144. Out of 144, only 2-3 values are outside, so I am not much bothered about 2-3 values out of 144 values. Okay, so roughly from the visual inspection, we can tell that, well, 4 conditions are satisfied. Now let us go to the statistical test, and in this case, statistical test gives me the p-value is 0.233. That means I can take I can say that the null hypothesis is accepted, and the null hypothesis was basically that residuals are white noise. So I can also testing of hypothesis, that statistical test also support the visual inspection, and now I can tell, well, the standard assumptions of the residuals on the residuals satisfied. So we are satisfied with the model. Okay. After doing all those things, I can now tell that based on the residual analysis, we are satisfied with the model, and the model in this case is basically the log of the time series basically follows the ARIMA model 011 and seasonal model 011 with frequency 12. Okay, so that is basically the analysis. Now let us see how the analysis look like over the ARIMA 2, which is basically done over the original data, with auto ARIMA function. So let me just run this one once, because if it changes somehow. So you see that again from the plots, things are roughly okay, because now again they are almost inside. But now the problem is again the variance, because now you see that the range is quite big. So the variance here will be quite large enough compared to variance here. And why this has happened? This has happened because I am taking e to the power. So values are actually, you see that after taking the log, the values of the time series is something like 6. So when you take e to the power, the values are in the range of 400, 500, so like 300, 400, 500. Okay, so that's why in this case I have bigger errors. when I am trying to forecast that, and you see that when I am trying to forecast some value like 500, 600, and maybe I can commit error of 40. That may happen. Okay, so from that perspective, that error of 40 is not that bad, or error of -20 is not that bad. But if you see the variance will be quite small here, but variance will be quite big here. So again, that variance is a little bit problem in this case, but again, for the time being, because of the range of the data is so big, we can easily check what is the maximum of air passenger data. What is the maximum of air passenger data? This is 622, and minimum is, the minimum is 104. So the range of the data is quite high, and compared to this range, this range is not that big. That's why for the time being also I am not looking into that so critically, but as I said, that may be improved using the better model. Okay, now ACF there is no problem because initial, most of the things are inside the band, only one is outside, I do not care about that. Similarly, the histogram is almost look like normal, only two problems are there. One is these two, that of course that are coming from this one and this two, and another somehow here the frequency is quite slow. So that are two small problems, but roughly this is also normal. And now that I can go for the test. Test is p-value is more than 0.1, so I can accept my null hypothesis, and that says that I am satisfied with my modeling. Okay, I am satisfied with my modeling, though there are small glitches, but as I said, we can just ignore them. See that as I mentioned in the last class also, that the theoretical things will not match with the practical things pi to pi. There may be some differences in that, but those differences we have to ignore, and that when to ignore, when not to ignore, that actually comes with experience. Okay, so any questions up to this part you can ask. Any question you can ask.
Sir, in ARIMA also, are we calculating regression coefficient using the OLS, ordinary least square procedure? Or
not ordinary, but some least square procedure. Ordinary least square procedure, of course, you can use, but normally some better method, which is called weighted least square, and all those things people also use. Yeah.
Sir, what is this maximum likelihood here procedure for calculating regression?
Well, maximum likelihood is basically, how can I tell? Okay, let me put it this way. So, likelihood basically means that kind of a probability, okay? So, I can put it, not exactly, but you can interpret it in this way, that probability of getting the data, okay? So, one of the way to estimate the parameter is to use the maximum likelihood method, and what we do in maximum likelihood method is that we choose those values of the parameter for which the probability of obtaining the given data is highest. Okay, and that probability, the maximum probability, is called the maximum likelihood, and that probability is given here. But as I mentioned, it is not exactly probability, but it is something close to probability, probability multiplied by something actually, and so that likelihood value can go outside the 0-1 range also. Okay, does this give the intuition or at least, or no?
Yes.
Actually, an exact thing if I have to tell you, then I have to basically take another 1 hour class actually. That's why I am just not giving it exactly. But that you can keep in mind, this is another way of estimation. That like least square estimate, least square is one way of estimation, this is another way of estimation. Okay, so now if any more question I can answer, or I can just proceed to the next thing. Okay, so let us proceed to the next thing. Yes, exactly.
Sir, in this thing, like variation inflation factor will not come into picture, no, sir?
Variation inflation factor.
Yes.
Yeah, that not coming into the picture, and exactly you are right that if you want to take those things, then basically you have to model the variance.
Okay,
and as I mentioned, Arch and BART, they are actually do exactly that. They model the variance based on the observed data.
Okay, sir. Okay.
Okay, that exactly do that.
Okay, thank you.
Okay, so so now let us talk about something which is evaluation of forecast. Okay, so finally one of our aim is to forecast. Okay, that means that as I explained that, well, I have, in our case we have data of air passenger up to the year 1960, December of 1960. Maybe I try to find out what is the forecasted value for the year, for the month July of 1961, or for the month August for 1962. So forecasting is one of the prime things, and I have to do this one. I have to check that how my model is working with respect to forecasting. Okay. So if I try to do this, I have to basically check how accurate my model is as long as forecasting is in the question. How I can do that? One way, straightforward way, I can tell that, well, I have, if the residual are little quite small, that should work. But the answer to this one is that is not a correct way to look into that. Intuitively, it look like that if the errors are small, then it should work. It should work. The forecasting should work quite well. But the answer to this, that may not be true. And the reason behind this is as follows. When I am doing this one, when I am finding out ET, what I am doing, I have basically the time series XT. From that, I find out some model. And when I fit that model, I am using all the values XT here to fit this model, to find out the parameters of the model. And from this model, now I am calculating the estimate. And then from the estimate and the original data, I am calculating the residual. So that means in this case, what is happening is that to calculate the residuals, I am actually using the data and then I am calculating the residual. But for the forecasting, that will not going to be the case. The reason is that if I have a data like x1, x2, up to maybe xn, then I may try to forecast xn plus 1. Or I may try to forecast xn plus 2 or something in future. So this is my data, this is my given data, and I may try to forecast something in future. So I will fit the model based on this data. I will fit the model based on this data, and then I try to forecast this one. So there is a basic difference between this error and the forecast error. Now the forecast error will be something like, if I forecast is xn plus 1, forecast for xn plus 1 is this, then forecast error should be something like this. But this quantity is unknown to me at the time point n. This quantity will be only known to me after we realize the value xn plus 1, after we see the value of the n plus first point. Clear this point? So just like this, that in case of our data, the last data point is 1960 December data. Now I maybe try to find out the estimate of 1961 July data or 1961 January data. So based on the data we have here, I have a model, and based on the model, I have some forecast. Now, whether the forecast is working well or not, that I can only understand when I have the data of 1961 January. Okay. So at the point of 1960 December, I cannot have the idea how good my forecast working, how good my forecast is working. Okay, how accurate my forecasting is. That I do not understand. Okay, more practical example is that maybe I try to estimate what is the price of a particular share tomorrow. So to estimate that price, I will use the data till today. And based on the data, I have a model, I estimate it today, I forecast it today, but I do not know how accurate it is. Only the accuracy I can understand if I reach tomorrow. And when I reach tomorrow, then I will have the data for tomorrow. Then I can tell how accurate it is. Okay. So that's why the forecasting accuracy cannot be estimated or cannot be assessed or cannot be judged based on the residual. I have to actually use the forecast error. And forecast error is this one. And definitely for future, I do not know these values because I do not know these values. Okay, so we have to do something else. What we have to do? What we basically do is that we divide the data into two parts. Some data we put into the training part and some data we put into the testing. What we do, we basically estimate the model based on this training data. I feed the model based on that and then forecast this part. Now, in the data, when I am basically fitting the model based on the data, then this data does not have any effect. As if we have data up to this point. So this is the current value, and this is the past value, and these are the future values. Now I try to forecast this value. Now when I forecast this value, I have the forecasted value as well as I have the real value. I can see how accurate my forecast is. Okay, so that is basically people do, and they divide the data into two parts. The most recent part kept into the testing data or testing set, and the old part is kept into the training data or training set. Okay, and as a thumb of rule is that about 80% data will be in the test part and about 20% data will be in the testing data. Okay, sorry, 80% in the training set and 20% in the test set. But this is a rule of thumb only, as I said. Variations are available, and that also depends on how long the data is, or how many data is available with me. So if I have a quite big data, maybe I can increase the test part little bit. If because if I have a very large data, that means if I have the data x1 to xn, and if this n is quite big, then even if I take maybe 70% of the data into the training set is still quite big. So the model fitting hopefully will be good. But if my n is small, then I should not make this training set is very small, because if I make training set is very small, the fitting will not be at all good. So that's why basically, of course, this is a thumb of rule, that 80-20 division, but variations are possible. And another point for forecast we should keep in mind is this one, that the test data, the length of the test data should be at least the length of the maximum horizon. Okay, the maximum horizon length at least should be there. The reason is that maybe based on the data I try to forecast, just for example, that this one, maybe based on the data I try to estimate what is the forecasted value of 1961 or July 1961. Okay, so that means July is basically 6 or 7. July is 7. So test data should have at least 7 data points. Okay, test data should have at least 7 data points, because the horizon in this case is basically 7 steps ahead I am going. So that is basically we should keep in mind, when at least for time series analysis we should keep in mind. Okay, so basic idea of this revision and all those things I hope is okay. Any question? Okay, no. So how we can do that? Some R function which are helpful to do this division is window, subset, head, and tail. So what window do? Window actually take a subset. Window and subset are almost equal. These two are almost equal. So they basically take a portion of the data. That portion may be the initial part. That portion may be something in between part. That portion could be some the end part. Anything can be taken. I will discuss exactly how that can be done. And what head do? Head actually take the initial part, some portion from the initial part, and tail take the some portion in the last part. These two I am not going. These three I am not going to discuss now. If you interested, you can easily check that there are a lot of good tutorial are there. I will only going to discuss this one. This window thing here. But I'll come to this one. Just before that, let us proceed and see how can we do that accuracy analysis. Okay, so now, okay, so some point of caution I should mention here, that is regarding the forecasting. The points are that a model actually fits this training part very well does not mean it will going to forecast the future very well. Okay, that may not be true, because something may change in the process. Okay, something may change in the future, so that may not be true. That's why the evaluation of the accuracy is needed. Then the next point tells that perfect field is very bad thing, because the point is that here, see, if I have some point, maybe if I have 10 points there, maybe if I have 10 points there, if I take a polynomial of order 11, that will exactly fit this data. Is that fine? Is that okay? Answer is no. The reason is that it is too restricted. Now the future data may come here, may come some other place. Okay. So the perfect fit is not good at all, as well as statistical analysis is concerned. Perfect fit is not good at all for forecasting. Okay. And this perfect fit is something called overfitting also. And as I mentioned, these 2 points, that perfect fit is very bad, and we can always get the perfect fitting by increasing the parameter, but that is not at all good in any analysis, because this is too rigid. Perfect fit is too rigid. Okay, so this thing I have already discussed that well. I divide the data into training part. I have key data point in the training part. Total data point is n. Divided into 2 parts. Training data point has t points, and the test data point has n minus t points. And then based on this training data, fit the model. You have the forecasted value of the points in the data in the test set, and then the forecast error is basically nothing but the distance between these two, the difference between these two. Okay, so it is look like residual. But the only thing is that in this case, only this part has been used to fit the model. These values are not been used. Okay. So once we have this error, we can talk about different measure of the error, which we can look into. So this is kind of a assembled error. So I have in this case basically how many errors are there? How many errors are there? I have basically again n minus t errors are there. So now how we can combine this t n minus t errors, and how can I check overall the quality of overall forecasting? So there are several methods are there. There are several measures are there, like absolute mean absolute error, which is nothing but you find out the error, the forecast error, you take the absolute value and take the mean of it. Similarly, you have root mean square error, which is nothing but you take the square root of the average of the square of the error. So these are kind of the same. In this case, basically see that error can be positive, can be negative. So if you do not take this absolute value, the problem is that positive error may be cancelled with the negative error. Finally, the average is small, but that may not be very fine thing, because this kind of thing may happen. Maybe the original data goes like this, but the one forecast come here, another forecast come here. Now here you have a positive error, here I have a negative error. The magnitude of them are same. So if I take the average of these 2 points, it will be 0. But I have a lot of error here. So that's why that taking mod is important. One way to take mod, or other way to take square, so that the sign do not have any role to play here. Okay, and if you take the square, you have to take the square root again to finally get some quantity which has the same unit as the unit of mean. Okay, then we have some kind of relative error also. This is basically you have error. This error is committed out of this original value. So this is a relative error, and then some average of the relative error can be looked into. Okay. And finally, this one is kind of a scaled error. Scaled error are important because you see the Q does not depend on the unit of X, because E has unit of X, this has unit of X, so unit of X actually gets cancelled. So if I have different time series given in different unit, first time series maybe in centimeter, second time series maybe in meter. So if I want to compare these two, of course, one thing I can do is that I can transform all those things to same unit, or I need to use some measure which does not depend on the unit, like something like that. And of course, in those cases, I should not use these three measures. I can only use these measures. Or other way, you just convert all the data into the same unit, then you do that analysis. Okay. And this can be done very easily with the accuracy function in R. And this is also in the forecast package. So we can easily do this one. Okay. So let us see how we can do. Okay. So first what I have to do, I have to basically partition my data. Okay. As I said, I have roughly, I have 444 data here. So what I did is that the last 2 years I have kept into the this thing I have kept into the, just a minute, just let us see the data once again. Okay, so what I have done is that up to this data I have kept into training data set, and the last 2 years I have kept into the test data set. Okay. So how we can do this partitioning? The partitioning can be done in this way. Training data set, I take the original data is air passenger data. I break it into, I take up to the point one. Oh, I am sorry. I have actually here, I have taken up to this one. So 3 years actually taken into the test data set. So start is basically from the starting point, that is basically 1949-1, and the end is basically 1957-12. That part actually, so this part actually give me the training data set. So let us execute this and let us see that whether actually I am getting this or not. I am getting exactly that up to the 1957 I have in the training data. Okay. Now let us see the test data also. So again, it has been done in the similar manner that for the test data, that data will start from this data point, which is basically nothing but 1958 January 1. So I start from here, and it will automatically end here. There is no point to give the end. Similarly, here I do not need to actually mention the start. If I give the end, it is enough. So test data having the 3 points. Okay. Now what we do? See, in the auto ARIMA, we have seen that the fitted model is basically ARIMA 212 with seasonal component 010. So what I did is that I fit the ARIMA model with the same order to the training data. And if I fit that, what I got is that we got this thing. And now I just go for forecasting. And in case of the forecast, you see that I have taken 36 future values because 3 years are kept in the test data. That's why 36, horizon is 36. And then I look into this one, and you see in the accuracy what I have to supply. One is the forecast, what forecast I got from the fitting, and another is the test data. Okay, these are two arguments. And when we do that, we have this result. And here several measures of accuracy are given. Some of them I have already discussed, and some of them I did not discuss here. So we have discussed RMSP. It is basically coming out to be 22. See, here the thing we need to look into the test data part, because the training data part is basically kind of a residual analysis. So that I do not care here. My main thing is basically test data part. That is basically the important here. So error is 22, which is not very bad in the sense that range of the data is going up to 600, from 100 to 600. So that's why this 22 is not very bad thing. MAE is basically, as you see, the MAE. So MAE we have not discussed here. Okay, MAE we have discussed. MAE basically this average. This average is basically turns out to be 12. This one is basically nothing but average without this mod. Without this mod, so that does not give me much input in this case. MAPE is basically this quantity, and MAPE turns out to be quite reasonable. MAAC is basically the scaled one. The scaled one, that is also quite small, quite reasonable, and that is actually very, very meaningful here, because see, in this case, RMAC actually do not take care of the range of the original data. The range of the original data, as I mentioned, goes up to 60. So data points are quite big. So in this case, because of that, 22 is not that big value. But because MAAC, I divided by that data, the difference of the data, so it somehow takes care of the fact that range of the data. And that's why this turns out to be quite small, and it is a quite meaningful measure in this case, that if the data are itself quite big, then little bigger error is fine. Like if I want to estimate something is of the order 1000, if I make an error of 50, it is fine. But if I try to estimate something which is of order 10, then making an error of 50 is very, very bad. So that's why basically this scaling thing is quite meaningful, and it shows that well our model for forecasting is not bad at all, which is quite good actually. Okay, fine. So using this measure, we can do that, and doing this thing is not at all difficult. Well, any questions? Okay. If not, quickly I go through another thing which is called cross-validation, which is basically some sophistication over the previous method of accuracy. So the previous method of accuracy, what we did, we partitioned the data into two parts. Here also we partitioned the data, but in a different manner. What we did is that here, when the first line I have, then basically these blue points are basically my test data, and the red point is basically the blue points are my training data, and the red point is my test data. So I fit my model based on the blue points, and then I try to forecast the red point. In the next step, this data I have observed, so I take this inside the training data, and then I try to estimate the next just immediate future. And then in the next step, this data has been observed, so I include this data into the training data, and then I try to estimate the next data point. And so on, the process is going on. Okay, so this one is called cross-validation, and when I do all the steps, I have an error here, error in this estimate, I have an error in this estimate, and so on. I have multiple errors, and then we combine those errors to see how what is the final cross-validation is. Okay, so this is that just one-step cross-validation. I can have 3-step or 4-step cross-validation like this. In this case, this is the training data, and based on this training data, I try to estimate, I try to forecast 4 steps ahead, these data points. Then I include one more data. I again 4 steps ahead. I want to forecast, and so on. We can proceed. So this is more sophisticated method for checking the forecast accuracy. This is called the cross-validation, and this also can be done very easily in R. So, and for that, the function is TSCV. TS time series, CV for cross-validation. So this is TSCV we have to use. And there, the only problem is that we have to give a function here. And this function is such that the first argument should be a time series, univariate time series. First argument should take a univariate time series. And this 8 argument, the horizon argument, should be there. And this function should return a forecast should return a forecast object. Should return a forecast object. Okay. So that way you need to write the function. I don't know whether you know how to write the function or not. So I am not discussing this one much, but just to show that it can be done here. If you want to learn, you just learn it by yourself how to write the function. So let me just execute this and let us see how this data look like. It will take a little bit of time. Yeah. So it is basically giving something like this. Something like this. Initially, you see some values are not estimated. The reason is basically here the initial few values needs to be used to estimate the model. So that's why this part cannot be kept into the forecasting part. So that's why these values cannot be, the forecast error cannot be find out, the cross-validation error cannot be find out for these values. Okay. After that, the values are given, and finally what is interesting is to see the combined error, and the combined error I can find out by this, and the combined error is basically this. It is nothing but I take the square of every error and then take the average, and this part is given just to remove this NA values. Just to remove this NA values, this part is given, and then it basically gives this 12. 12 is again not very bad compared to the range of the data. Okay, 12 is not at all bad compared to the range of the data, and also using the cross validation, we can also see that our model is quite well for forecasting. Okay, so with that I just stop, and here are some references. So the first reference is basically a book on time series, and that in this book basically forecasting aspect of the time series are addressed. And it's a quite nice book. You can see it, and this book also talk about little advanced modeling like arts, crouch, all those things. This book is talked about. And then there are two references. These two references are for two important packages in R which are used to analyze this time series. One is forecast and another is T series. So you can see these references. And with that, I stop. If you have any question, you can ask.
Sir, I have one question.
Yes,
We also have ARIMA model. If we are able to
Yes.
deal the seasonality here, then right, why we go for ARIMA?
Yes. So your question is that what is ARIMA model?
Yes, and why we are going for that if we
Right.
already
So,
can deal the
yes,
seasonality? Yes.
Okay, that I have not addressed exactly here. That's why I skip that part. The idea is basically, see, in a time series, you can decompose it. Decompose means you can separate out the trend, you can separate out the seasonality, you can separate out the rest of the part. Okay? So the ARIMA model actually we use on the last part. On the seasonality part also you can use some modification of the ARIMA model, and that is called ARIMA or seasonal ARIMA. Okay? So more detail I cannot give into so short time. So I request you to go through.
Yeah. Yes. Thank you, sir. I have another question, sir. Right. We have various models like Halt's model, Winter's model, Gray forecasting models. Right. So companies are using actually which model they are using?
Which case you are talking
For
about?
forecasting.
That completely depend on data. So those models, they have some background model. Actually, I do not remember all of them. For example, what we can remember, there is something called exponential smoothing. Okay. In case of exponential smoothing, they actually do some kind of use of the geometric progression. Okay. The parameters are in the geometric progression. So that model they use. So there are a lot of different models for forecasting. I have actually in this here actually discussed one of them in detail, that ARIMA model. There are a lot of them. Now, if you ask me the question that which model you should use, that completely depends on the data. And on the data, you feed several models, see the residual analysis, see AIC, see BIC, see forecasting error, and based on that, you basically have to find out which model is working, which forecasting model is working both. Okay, and that model you need to use for that particular data.
So it means that companies are using the mixed of models, right?
Right.
Not they are sticking to
Yes,
the one.
absolutely true. The mixing can be done also. Many things can be done. Yeah, many things can be done.
Because
And
each
for
and every company is forecasting right demand for the demand of their products.
exactly. That's what. See, one mixing we have already talked about. ARIMA is itself a mixing of AR and ME. Right. So all such kind of mixing can be done. Or sometimes what happens is that when you decompose a time series, maybe one part, maybe that seasonality part is quite good explained by a by ARIMA model, and the error part may be quite good explained by a different model, maybe Gauss model, maybe exponential smoothing, maybe something else. So that kind of thing also come into the picture. Different part is forecasted nicely through different models, and then finally we just club everything together to give the final forecast. Okay, so that's what these are completely depend on data, and that only comes through the expertise. If you work with the data for a long time, then only you will have these insights. Otherwise, it cannot be given in a class, only in two classes or three classes. Okay, any more questions? Okay, if not, over to Professor Shairam.
Yeah, thank you, Ayan. Thank you. Thanks a lot. So again, we'll meet you again in the second session, second half.
Second half, yeah.
So we'll take a short break now. So the next session will start at 11:30. So maybe can take a short break. And I can see that the second